Video, we're going to be taking a look at 2.3, mouthing off and nosing around. Now, we're still looking at these characters, these that we're designing on the computer, and we're looking at the familiarity of them, and we're looking at different parts. They're obviously their nose and their mouth. That's why this is called mouthing off and nosing around, and we're looking to determine if they're familial, meaning they're of the same family, in ways that they are, meaning we call it in mathematical that they are similar. So that's one of our words that we're going to be looking at here, the word similar. And we need to make sure that we have an understanding and a definition of that word in our notes. So right now, make sure you have that somewhere in your notes. We've talked about it several times, but similar essentially means these two things right here. The side lengths of one figure are multiplied by the same number to get the corresponding side lengths of the other one. And so if you have this shape and has all of these coordinates given to you as x, y, and it can be multiple coordinates, and you want to create a similar figure that is, let's say, 3 times the size, then you would multiply both your x and your y by 3. And that grows it both horizontally and vertically. Make sure you have this down as well, that this x right here, this is your horizontal change. Right, so if you multiply the x by a number bigger than 1, that makes it wider. If it's between 0 and 1, that means a decimal or a fraction that makes it skinnier. And the y is your vertical change. Make sure that's somewhere in there. Highlight that. That's extremely important to understand as we continue to learn about these things. And then also for similar, the second part of that is the corresponding angles have to be the same side. Like up here, if you look at these angles, like look here, these two guys are similar to each other. Those two angles are the same. However, if you look at this angle is different than these. This angle is more open or wider or bigger than these two angles. So we already know that this guy is not similar just looking at that angle. Make sure you have the definition for similar, what it means to be similar, in your notes. Pause the video as you need to get that in there and highlight it, because that is a key understanding. Now let's take that idea of what it means to be similar and how to find similar shapes, more specifically right here. This number that I multiplied the x and the y by, that is what we are going to be calling the scale factor. So right there and right there, those are the scale factor. It tells us how much we are going to enlarge this figure or shrink this figure. Again, if the scale factor is bigger than 1, then it gets larger. If the scale factor is less than 1 but greater than 0, then that gets smaller. Okay, so it has to be less than 1 but greater than 0, because you can't have negatives. Negatives, we're not working about negatives right now. We don't have negatives, doesn't make it smaller. Okay, so that's your scale factor. Down here is asking you to define it, gives you the definition. It's the number that the side lengths of one figure can be multiplied to give the corresponding side lengths of the other figure. And the most important part about this definition, have this definition in there, but the fact that they're multiplied. All right, the scale factor is always a multiplier. So write that down. It's never what's being added to it. It's always what's being multiplied to make that figure that much bigger. Okay, the scale factor is always that number that's being multiplied. And go ahead and take a minute and jot this down, copy this down in your notes. That way we can talk about it. So pause the video, copy that little chart down there, those pictures in your notes, and then we'll talk about it. And you might want to, once you have that copy down, you might want to also grab a couple colored pens and pencils, or highlighters would be the best, because we're going to look at these ideas of figuring out sides that are corresponding, and then how that scale factor helps us find those corresponding, the new lengths of the corresponding sides. For example, on this rectangle, that one that I highlighted, the 2 centimeters, is clearly the shorter of the two. Meaning on the big rectangle, the shorter of the two is its corresponding side. Should be pretty straightforward to figure out which are corresponding. Then this longer one right there and this longer one, those are corresponding. So I highlighted them accordingly so we know which ones correspond together. Now, look at the scale factor. To go from 2 to 6, we multiplied by 3. This is our scale factor. Okay, that's our scale factor. And you notice we also multiplied by 3 on the other side because we want that next shape to be similar. So if we multiply everything by that scale factor of 3, then this is 3 times the size. Or it grew by 300%. Because some of these questions are going to ask you specifically by what percent did this grow. Okay, so make sure that you can do that. Now down here, to address this question down here, what's the scale factor from the larger to the smaller? So now you're going the other way around. Well, from the smaller to the larger, the scale factor was 3, but now let's say we want to go from here to there, the scale factor is now 1/3. To go from 9 to 3, the scale factor is now 1/3, right? And 3 and 1/3, those are what we call reciprocals. All right, make sure that's in your notes. The reciprocals are going to come up time and time again. But in order, if you go from one shape to the next and find that that's like a scale factor of 3 in this case, and then you want to go backwards from the big one to the small one, the scale factor is just the reciprocal of that other one. All right, so jot that in your notes. Make sure you have that. And also there is a lab sheet that you should have gotten or that is on my website that you can print out if you want to. You don't need it, but it'll allow you to draw on this page that I'm looking at here. And we're going to do something a little bit different because we're going to do A kind of all at the same time because it asks you to find which pairs of rectangles are similar. We're going to do that first, and then for each pair we're going to find scale factors, look at the perimeters, and then look at the relationship between the areas. And we're going to set up a table when we do that. So the first thing that I want you to do is I want you to identify which of these are similar. So we're just looking at these rectangles. All right, use what you know, identify which ones are similar, and then come back to the video. Okay, so if you tried this on your own, you should have been able to identify these 3 that are similar. So J, L, and N are similar to each other. Okay, that means they're the same shape, different size. K, it's a different shape. Okay, it's similar shape, but it's different. It doesn't increase each side the same rate. So we do not include K or M. So we're not looking at those to answer these questions. Next thing that you're going to need to do is find the side lengths of all of these shapes, the 3 similar ones. So go ahead and find the side lengths and perimeters and areas. So you're finding side lengths, perimeters, and areas for these 3 shapes. Okay, so go ahead and check your answers just to make sure you have all of these correct. The area of the first one is 16 units squared, and it's units squared because you multiplied 2 dimensions, which is length and width, to get that. Perimeter is 20 units. Make sure you're labeling these. I will mark them wrong on quizzes and or tests. And then the second one, L, is 4 units is the area, 4 units squared, and the perimeter is, this should be P, not A. Those are P's. And the perimeter of the second one I said is 10, and the perimeter of the third one is 30 units. Make sure you have those and that those are accurate. And now I'm going to help you set up a table to answer the rest of these questions for part A. And let's go ahead and set up our table to look something like this, where we have that we're looking at the rectangle comparisons, right? Like we're looking from J to L, what's the scale factor? From J to N, what's the scale factor? And from L to N, what's the scale factor? All right, so then all of your columns would be then scale factor, side length, perimeters, and areas. Go ahead and pause the video, set this up, and then come back and so we can continue filling this out. Now, when we're looking at the scale factor from J to L, all right, now to go from J to L, if we take a look back at this picture right here, so we're going from J to L. So we're looking at the scale factor, and so we are, nope, I don't want that, I want this. There we go. We are looking from, for example, 8 to 4. Those are corresponding sides. What do we multiply? That, remember, scale factor is always the multiplier. What is it that we multiply to go from 8 to 4? What is it we multiply to go from 2 to 4? And they should be the same thing because that will give us our scale factor. And in fact, we multiplied by 2. And so 2 on that one is going to be our scale factor. And we go ahead and we're going to do that for all of these. So 2 is our scale factor here. And then go ahead and do J to N and L to N. Okay, so if we take a look at J to N, we are looking at the scale factor. So we're going from, for example, 4 to 12 and 1 to 3. That is, this is L to N that I'm looking at here. So L to N, the scale factor is 3. Okay, so that is our scale factor. We're going to put that on our chart. But now if we go from J to N, this is a little trickier, right? Our scale factor, you're going from now 8 to 12 and 2 to 3, and that ends up being 1.5, but we're going to write that as 3 over 2. So L to N is, our scale factor is 3, and J to N, our scale factor is 3 over 2. All right, so we have those in there. And now I just want to point something out real quick. I'm not going to spend too much time on this, but at the beginning we learned that you can reverse this. So instead of going from J to L, you could also go from L to J. And the scale factor would be the reciprocal. So if we went from L to J, the scale factor would be 1/2. If we went from N to J, the scale factor would be 2/3. And if we went from N to L, the scale factor would be 3 over 1. I just want to point that out, that all of these can be reciprocated if you want to go the other way. So if on a quiz or a test I say, what's the scale factor from L to J? The answer is 1/2 and not 2, because you are going from a bigger shape to a smaller shape. So you should be able to recognize that I'm multiplying by a fraction in order to get that smaller shape. Okay, now what I want you to do is we're still focusing, let's ignore those ones that I just did in there, and we're still focusing on these. Oops, thought I hit that. There it is. So we're still focusing on these, right? So what is with the scale factors 2 for J to L, what's the side lengths, right? What's the scale factor for the side lengths? And that's what you're looking for there. And we should already know that because the scale factor for the side lengths is always going to be the same. So the scale factor for the side lengths is 2, 3/2, and 3 as well. So they're always going to change at the rate at which the scale factor defines it or tells it to. Now look at the perimeters. Compare the perimeters and figure out what's the scale factors there. Meaning, hey, let's take a look at, like, for example, the perimeter of, let's do this color right here. The perimeter of J is 20. The perimeter of L is 10. What do I multiply to go from 20 to 10? And do all of those for the perimeters. Pause the video, do those, and then come back. And you should have found that you get the exact same change or scale factor for the side lengths. So the perimeters are just the sum of the side lengths, so that makes sense. Now let's take a look at the areas. Okay, now we're going to do the same thing for the areas in that we're going to, whoops, wrong one. compare the areas together and try to figure out what is the rate at which they change with those. So you're looking at from 16 to 4, for example. That would be how much did that change? So from 4 to 36, how much did that change? From 16 to 36, how much did that change? Go ahead and figure out what those changes are, what those scale factors for the areas would be, and then come back. All right, so hopefully you were able to pause the video and go and figure out what these new areas would be. And actually to go from J to L, it was a scale factor of 4. To go from J to N, it was a scale factor of, if you simplified it down and put it as a fraction, of 9 to 4, or 2.5. Either one of those would work. And then to go from L to N, that was a scale factor of 9. Now, if we look, these are different. Everything else, the scale factor to side lengths to perimeters, all of those had the same value when we were scaling it by 2, by 3/2, or by 3. Right? So the side lengths and perimeters are related. But if you double the side lengths, like if you look up here, we are doubling these side lengths from J to L. We're doubling these side lengths right here. That means that you more than double. You double the area. Okay? So doubling the side lengths will take the area times 4. From L to N, we tripled the side lengths. Right? But it way more than tripled the areas. So you have to be really, really careful. And in fact, the relationship between these, and I want you to write this in your own words. All right, you ready? When you take a scale factor to a shape, the side lengths and the perimeters are going to change by that scale factor's multiplier, right? So if the scale factor, for example, is 2, then the side lengths and the perimeters are going to change by that scale factor. The perimeter will double, and the side lengths will double if it's by 2. If it's by 3, the scale factor is 3, then the side lengths and the perimeters will triple. However, the area, okay, I want you to write all of that down. Pause the video if you need to. Write that down. The area is going to change by the square of the scale factor. Okay, so right here, write this down. If you need to put an example, okay, put the example. You can even do a quick little example down below if you need to. Try it. Like if you have a side lengths of 3 and 4 and you triple the side lengths, look at the areas. What's going to happen to the areas? All right, so put an example in your definition. If you need to highlight this over and over, this is another key understanding of this lesson. And that's all for this chart. And that pretty much answers all of part A. On part B, it just says which pairs of triangles are similar. And I want you to go ahead and answer all of part B on your own and see how you do. And then come back. So part B is the same thing. You're doing the same thing, but now you're doing it with the triangles. Okay, so you should have that triangles O, R, and S are the only 3 that are going to be similar to each other. So we're not even going to look at or consider P and Q since they're not similar or part of this family. Those are only 3, and you should have the scale factors. Again, you can have them the other way. You know, for example, from O to R, scale factor is 2. But if you go from R to O, the scale factor is 1/2. So if you have from R to O and hence the scale factor is 1/2, it is not incorrect. Okay, and then if you go from R to S, that's 3/2. And then if you go from O to S, that is a scale factor of 3. All right, so make sure you have all of those. That tells you which triangles are similar. And then part 2 says down here, for each pair of similar triangles, find the scale factor. And that's what we just did. Then find the area of each triangle. So let's go ahead and find the area of each triangle. If you haven't done that, pause the video and you need to do that. So if we look at those areas, I have the areas of O up here, is going to be 1/2, because remember the area of a triangle is 1/2 the base. So 1/2 of 2, which is 1, times the height. Oops, sorry, that's going to be 1. 1 square unit for that one. So half the base times the height. And then half the base here is 2 times the height, which is 2. That's 4. Half the base here is 3 times the height, which is 3. And then that gives you 9 square units. Go ahead then and for the next one, it says find the areas. Does the same relationship between scale factors, similar rectangles, and their area apply? Okay, so if we take a look at that, remember it should be the square of the scale factor. So if we look at the first one, you get a color here, it's going to be purple. If we look at the first one, O to R, scale factor of 2. Well, the scale factor is 2, so the area scale factor should be 2 squared, which is 4. So this area right here should be times 4, which it is. Whoops, down there. There we go. Okay. And then if you're going from, let's say, O to R. So if we look at O to R, I'm going to do this down here. So with O to R, the scale factor was times 3. And so the area for O to R should be times 3 squared, which is 9. And the area of O was 1. The area of R is 9, so it checks out. And then the last one for R to S, I'll do this one over here. From R to S, the scale factor was 3 over 2. And so now if we're looking at the area of the scale factor from R to S, that should be times 3 over 2 quantity squared, which is 9 over 4, or 2.5. So if you take 4 times 2.5, that does in fact give you 9. I'm sorry, no it doesn't, because this is 2 1/4. This right here is 2 1/4, but if you take 4 times 2 1/4, that gives you 9, because times 2.5 is actually 10. All right, so yes, all of these check out. So the area is going to be square. The scale of the area is going to be square of the scale of the sides. All right, so if you know the scale of sides is 3, the scale for the area is going to be 9. Okay, so that checks true. And then draw 3 right triangles such as that exactly 2 of the right triangles are similar. I'll let you do that on your own. And then if you haven't, go ahead and answer part C. So again, if you have not paused the video and tried this on your own, please do so. A lot of these questions we've already talked about in our discussion in the last 23 minutes. So please try these on your own. It's extremely important that you try them on your own and don't just wait for me to tell you what to write. It's really important you try these on your own first. So if you haven't, pause now. Okay, and the first one, it talks about Marta and they now agree that J and L are similar. Right, so if you look at your diagram, J and L are your top 2 left ones where we found that the scale factor was 2. So Marta says the scale factor is 2. Jack says that it's 0.5. Are either of them correct? Now remember, yes, both of them are correct because it doesn't specifically say J to L or L to J, right? Because remember, the J is 2 times the size of L, but at the same time, L is half the size of J, right? So when we go from this to here, we said it was times 2, but you could go in reverse and it would be times the reciprocal. So in this answer, use that term reciprocal. Make sure that's in there. Make sure it's in your notes when you answer that question. And that is right there. Number 2, explain how to find the scale factor from a figure to a similar figure, right? You would just take the sides and find the quotient of the sides. Find the quotient of the sides. All right, so for example, if you're going from 3 to 4, 3, 4, and let's say that this is bigger, 6 and 8, then the scale factor would be 6 over 3 or 8 over 4. You would take this divided by that, this divided by that. Or you could go the other way, right? If you're going from big to small, you would go 3 to 6 or 4 to 8. Okay, you would just find the quotient, and remember, quotient means division. Find the quotient of the sides. Pause the video, write that down as you need to. Number 3, does the scale factor change the angle sizes? No. As long as every side is being multiplied by the same value, no, it's not going to change. And it just changes the size, but it does not change the shape because we're multiplying everything by the same number. All the sides are being multiplied by that same scale factor. So that is your explanation. And number 4, you have used rubber bands and coordinate graphs to make similar figures. How does the scale factor show up in each of these methods? Well, let's talk about the rubber bands real quick. When you had the rubber bands, right, you had this rubber band and then it was connected to this rubber band. Well, there were 2 rubber bands because you were drawing here and there were 2 rubber bands and it made it twice the size. If you had another rubber band in there, right, and still focus on this one, tracing your shape right there, it made it then 3 times the size. And then we did, multiplied by 150%. Well, that's a scale factor of 1.5. So if you can change all percentages to decimals as well. All right, make sure you really understand. Remember, this is a big story. In this story, everything relates back to itself, back to something we've talked about before. Make sure you are understanding all of these key understandings that we've been talking about, that I've been telling you to highlight over and over again, and how they relate to things that we've been talking about and doing and putting those into practice. Okay, so this is it for 2.3, mouthing off and nosing around.